Yes, thank you so much for inviting me. I'm very excited to tell you all about some of the work I've been doing over the past few years, specifically how I learned to start worrying and love smallest galaxies. And of course, as with any project, this would not have been possible without an excellent group of collaborators, which may or may not need to be updated. And so first, before I get down to why I love small galaxies, let's talk about what small is. What do I mean by small stuff? I'm a galaxy formation theorist, but there may be planets people, stars people, particle people. And so maybe you don't think of galaxies as very small, but just to give a sense of scale, I'm going to start out with our own Milky Way, almost 10 to the 11 solar masses. It's very large. It contains us, of course, and it's very wide across, 30 to 50 kiloparsecs, which is huge. It looks very much here like a very blurry picture that someone invented. But if we want to look at a real galaxy, we can then go to our next door neighbor, Andromeda. Now, Andromeda is even more massive, 10 to the 11 solar masses. And these are far from the largest galaxies in the world. I think I was seeing on Twitter sometime recently people's just existential dread at this IC 16, 13, or 18 and how much more massive it is. But let's not go up. Let's go down. I'm going to talk about the small stuff. If we zoom in to this plot here, and then zoom in again, now we're starting to get to the level of galaxies that I want to talk to you about today. Not quite, though. This is the LMC. It is a dwarf galaxy, but it's much more massive than the galaxies I'm going to discuss, 1 billion solar masses, and yet, a fraction of the size of its Milky Way, of which it's a satellite. Then we have Sagittarius. Now, Sagittarius is currently plunging through the disk of the Milky Way. It's been tidally stripped and stretched out, so it's very large on the sky, but it has about the stellar mass that I'm interested in, but at some point was much more massive. So let's zoom in again, and zoom in again. Okay, now we're finally at the scale that I'm talking about. We've got Draco. This is about the stellar mass that I'm going to focus on the high mass end. So it's a classical dwarf spheroidal galaxy, several 100,000 stellar masses in stars. But there's even smaller galaxies. This is on the lower mass end of what I'm going to discuss today, the ultra-faint galaxies. This is the lowest mass, I believe, or one of the lowest mass galaxies ever discovered. And you can see it here on the sky, or rather you can't see it. You can see where you might see it if you were able to see the stars. These things take many complicated algorithms to determine membership, but this is an ultra-faint galaxy. So these are the types of galaxies I'm going to discuss today. And it's a really amazing time to be in the field of dwarf galaxy formation, particularly observationally. We've known about dwarf galaxies. This is a very nice plot from Josh Simon's recent review, confirmed or candidate Milky Way dwarf galaxies. And we've known about these objects for quite some time, but you can see we just sort of trickled along, finding new ones every few years, until the whole dwarf galaxy world was revolutionized for the first time, I'd say, or one time recently, by the advent of digital surveys like Sloan. But now, with DES, with Pan-STARRS, HyperSubPrimeCam, and even with Gaia, we're currently going another revolution in low-mass galaxy formation detections, and specifically this time at the low-mass end. And it's only going to get better or worse, depending on how much you like these objects, or how much you think they're causing problems, with the next generation of ground and space-based observatories. LSST coming online very soon should find many more of these objects, and of course we're going to need a lot more analysis. So we're about to not only find more and more of these things, I would suggest, but learn quite a bit about them. So dwarf galaxies are cool in and of themselves, but they can teach us about a lot of things. Dwarf galaxies can teach us about the very nature of dark matter. I'm going to spend probably the majority of my talk going over this point. But dwarf galaxies can also teach us about the cosmic reionization background and also about star formation and feedback, because they're very sensitive basically to anything you throw at them. So if I drag a little too long into this part, don't worry, these other two parts won't be as long. So dark matter, okay. As we know, every galaxy, we believe, lives in a giant triaxial ball of this mysterious substance called dark matter. Dark matter is a really funny thing because we don't know what it is. We don't know what particle is. We don't even know if it is a particle, but we know an awful lot about it. To quote Paul Rumsfeld, I think this would be a known unknown, would be your dark matter. It interacts through gravity. It's pressureless, which is what allowed it to clump together in the early universe. The cold part of cold dark matter means that it was non-relativistic, allowing it to form smaller and smaller clumps, and it does not shine or reflect light, which makes it very difficult to, of course, detect and measure. But luckily, it has, of course, an impact on baryonic matter, which is helium, hydrogen, stars, planets, you, me, everything in the periodic table. Oh, I hope my volume is off here. Okay. Oh, no! All right, so this is a cool video with a little sound, and I'm just going to stop. There. Oh. I can't turn, the problem is I can't turn the volume off unless it's unplugged, so that's why I didn't just immediately do that. So let's try that again. Oh, that was cool. Yeah, it was cool. Huh? I should have kept it on. All right. Oh. Okay. All right. So, in the early universe, dark matter began to clump together, and it formed structures very specifically according to our best standard framework, Lambda-CDM. And as you can see in this, we can make massive computer dark matter-only simulations of the exact way in which it's supposed to cluster. And this is a prediction of Lambda-CDM. But because dark matter doesn't shine or reflect light, how do we test this? Okay, whew. Oh my goodness, okay. Probably skipped half what I was supposed to say. But anyway, okay, so Lambda-CDM predicts how dark matter should be structured and clustered, but we need to use what we can see to test this. Luckily, we have now, with the advent of these surveys, such as Sloan, which is mapped, I think, like a third or more of the sky, we know how galaxies actually cluster in space. So we should be able, if we assume, remember, that galaxies form in these dark matter halos, we should be able to test our model with these galaxies. Of course, we ran into a problem. How do we know which galaxy goes in the dark matter halo? And like any good physicists, we just did the dumbest thing possible, and we said, let's just assume the biggest galaxy goes in the biggest halo and see what we get. And doing that simple or dumb thing, whatever, the initial simplest thing, called abundance matching, does a really good job of predicting dark matter structure across large scales, Milky Way and larger. This is a huge chunk of the universe. So one of these objects is, or one of these images is the real universe, the structure of actual galaxies. The other is a mock universe made from the Bolshoi simulation. And I'm going to ask you guys to guess which is which. We're looking for team real universe. Who thinks the real universe is red? No one's, okay, who thinks it's blue? All right, if you guys were at my talk last, when I was here at the KITP, that's not fair. Or maybe you saw the man here. I flipped it upside down and switched it around, so usually that gets you. But anyway, the point is they're statistically indistinguishable. Lambda-CDM does a fantastic job of predicting the way galaxies should be clustered on large scales. What about the small scales? See, dark matter, according to Lambda-CDM, behaves in a hierarchical manner, right? So these giant clusters have halos. These halos have subhalos. So if we take a dark matter halo that we expect should host the Milky Way, that's still where abundance matching is going to work really well. And we zoom in on it. Should be, yeah, this is the Via Lactea simulation. So this is what we would expect to host a galaxy like Andromeda or the Milky Way. We can see that Lambda-CDM predicts that it should have hundreds or even thousands or even 10,000s of these tiny other subhalos orbiting around it. However, if you look out into the real sky around the Milky Way, instead of hundreds or thousands of satellite galaxies, we only see about 50. This is known as the missing satellites problem. And if any of you guys find yourself like groaning and getting tired, why is someone talking about the missing satellites a problem again? Well, you're not alone. In fact, I once heard Carlos Frank say he would leave the room if he had ever heard anyone mention the missing satellites problem again. Yes?
I'm not in this field, but I came across a paper that seemed to me, I can't be critical about it, but it seemed like it was really sensible. And it said, I don't remember whose it was, but it said, we took somebody's simulation and we put in the physics by hand because we can't do astrophysics that well, and the tidal field kills off the satellite. Is that true?
Yes. I mean, that's been shown. There's been a few papers, including by people. at UC Irvine. They've shown that it destroys not only galaxies, but the actual subhalos themselves. So that's one way to do it. But to be honest, you don't actually need to do it. And in fact, Andrew Wetzel was here at the KITP, at the Gaia conference, and I think he repeated 4 or 5 times, there is no missing satellites problem, standing from about right here. And even without the destruction by a disk potential, it's true down to the point at where we're observationally complete around the Milky Way. So down to about 10 to the 5, and I'm just going to try to promote this sort of new jargon. We always need new jargon in astronomy. So this is James Bullock and Mike BK. We're talking about bright dwarfs at the very high mass end, your LMC, SMC. Classical dwarfs, these are a few million solar masses, and then ultrafaints. For bright dwarfs and classical dwarfs, there really is no missing satellites problem. They match, it's within error between, so this is the number of galaxies as a function of stellar mass, and it matches surprisingly well. And this is, without any tweaking necessary. But look at the ultrafaint dwarfs, right? We don't know yet how many ultrafaint dwarfs are around the Milky Way. We're certainly not observationally complete at this mass level. And even more, we don't even know the number that is really predicted by Lambda-CDM. Right? We know about 14, but how many will we see? 100? 200? 300? Maybe in the next few years we'll find out. So this is one of the ways that dwarf galaxies can tell us about the nature of dark matter. Even counting them up and comparing them to our best theory can help discriminate between 2 different dark matter models. So here we have CDM, which is what I've been talking about until this point, on the left. And for CDM, even if there aren't that many tiny dwarf galaxies, it may not be a nail in the coffin for CDM, because we don't expect every single tiny subhalo to have formed stars or formed a galaxy. We expect that when the first stars did form, they heated up the intergalactic medium to a certain temperature that prevented these tiny dark matter halos with their shallow potential wells from holding on to their gas. So that's the solution for Lambda-CDM. If that doesn't work, there's another solution. We just change our dark matter model. If the dark matter particle is a little less massive, a little warmer, then there's a cutoff in such that these tiny dark matter halos don't even form at all. So what I want to do, and one of the things, kind of the themes I'm going to say, is run these Lambda-CDM simulations to see, can we fix this within Lambda-CDM, or do we need to throw out our model altogether? Now, there are other people in the FIRE group running simulations with warm dark matter. I'm going to stick to cold dark matter, but yet we can learn about the nature of dark matter. However, if we're going to make a firm testable prediction for the number of satellites that we expect to see around the Milky Way, which is the only way we're going to be able to test the theory, well, then we need to know what's the minimum mass for galaxy formation. So even though we know that the smallest halos will never form stars, we don't know if there's a sharp mass cutoff below which a dark matter halo cannot form a galaxy. And if there is a sharp mass cutoff, we certainly don't know what that mass is. And that's quite, I think, striking in 2019. Of course, there was, way back in 2008, a little bit of a suggestion that maybe we do know this mass scale. Louis Strigari measured the dynamical mass based on the velocity dispersion within 300 parsecs for all of these satellites of the Milky Way, dwarf spheroidals, over, I think, nearly 5 orders of magnitude in luminosity. And Louis found that they had the same dynamical mass. They're consistent with occupying dark matter halos of about 3 times 10 to the 9. Now, one sort of conclusion that was put forward is, well, that's it. That's the minimum halo mass. Coral, what are you talking about? This is it. It's 3 times 10 to the 9. However, there is an alternate explanation, and is that it is a selection effect. If you have these galaxies with the same velocity dispersion, if for some reason maybe supernova explosions or heating of some sort, there's a floor on the velocity dispersion. If you take that stellar population and put it in a lower mass dark matter halo, as James Bullock showed in his 2010 paper, then it puffs out. The half-light radii becomes much larger. It becomes more dim.
Are you also assuming that the velocity dispersion profile is flat?
Yeah.
It's all measured within 300 parsecs.
Yeah, there's quite a few assumptions that go into this. It's maybe not the best. I think there's been improvements to the modeling. But I think it is interesting to note that if for some reason there's a floor on your velocity dispersion, if you have galaxies in lower mass dark matter halos, they may be invisible. James called these, another clever name. We're all kind of known for that. stealth galaxies, and there might be hundreds or thousands of them. Okay, so how do we go about figuring out this problem, right? We can't just we don't have enough ultrafaints to do this abundance matching thing. It clearly doesn't work. So the way I want to go ahead and solve this problem is to run a different sort of simulation, one that actually forms these tiny galaxies, right? Fully hydrodynamic, gas physics, star formation, and that with enough detail to actually simulate the tiny galaxies of interest. Now, if to really simulate ultrafaints with a lot of resolution, it's still really computationally prohibitive to do something on this mass scale. This would be a Milky Way Andromeda sort of pair. So to kind of sidestep the issue for now until we can get faster computers, I'm going to cheat a little and zoom in on an isolated dwarf galaxy. So I just want to be clear, there are no Milky Ways in any of my simulations that I'm going to show you today. They're far away from a more massive neighbor. These are dwarf galaxies. Dark matter halos of about 10 to the 10 solar masses. Now, these are large enough that we think we know the type of galaxy that forms in them, something of about 1 million solar masses. And because dark matter behaves hierarchically, again, these things have their own subhalos. You can see that even a 10 to the 10 solar mass dark matter halo should have substructure. Some of them are less than this 3 times 10 to the 9, right? So if I'm trying to find out if it's possible to form galaxies in low mass dark matter halos, they're massive enough or low mass enough to be interesting. And we might be able to predict whether or not dwarf galaxies have satellites. So that's basically what I've been doing for the last several years, starting with my thesis and moving on through Caltech. I've been part of the Feedback and Realistic Environments, or FIRE project, with code primarily written by Phil Hopkins. And FIRE is a code that has all the bells and whistles. It's primarily particle-based, although it's a slightly more complicated hydro solver. But its kind of crowning achievement was to be one of the first to really get sort of realistic feedback. Now, feedback is when a star forms, it's basically energy, mass, and momentum fed back into the surrounding gas from that star, and it includes both radiation pressure from young massive stars, stellar winds from AGB type stars, ionizing radiation both locally and cosmic background, and then of course the supernova here. And you can see this every time this sort of puffs up there, that's the supernova exploding, really puffing up that gas. And one of the sort of hallmarks of the dwarfs in FIRE is that they're very bursty. They're having a lot of expulsions of gas. Oh, another cool thing about FIRE, is that it allows us to push to very high resolution, higher, especially the new version. So I'm just going to kind of give a sort of survey of resolutions up until what I've done. Of course, actually it's changing every day. There's people are pushing down on resolution. And so when we have a particle-based simulation, we talk about your dark matter particle mass, your, I say star particle mass, but it's really a gas or baryonic particle mass that then turns into a star when it reaches certain conditions, and then spatial resolution, or the softening length between the simulations. Before my 2015 thesis, your typical dwarf galaxy resolution still had a baryonic particle mass of, well, 10 to the 4, which you could do a lot with. It's very interesting, but remember, the galaxies I'm trying to form are 1,000 solar masses, so you're not going to be able to do that much structurally with a gas particle mass or star particle mass that's larger than your. Okay, I was going to get the video to go again. Okay, that's larger than your galaxy. So in 2015, in my thesis, I pushed it down to what were then the highest resolution cosmological zoom-in simulations run to redshift 0, 250 solar mass baryonic particle, and just about a parsec spatial resolution. And we did, I think we were able to look at a lot of things about the dwarf galaxies, but again, we're talking about tens of particles for an ultrafaint. So we tried to go even higher. So my latest paper, which is you can find on the archive here, is, so I think I was just beaten out recently. So it's the highest spatial resolution cosmological zoom-in simulation ever run to redshift 0. There's another one out that has 20 solar mass baryonic particles. But I want to point out this spatial resolution is it's sufficient to resolve the internal structure of within the blast radius of an individual supernova with 100 elements. So this is important because the inability to resolve this Sedov-Taylor phase of expansion in a supernova has led to a lot of sort of debates on how you handle that subgrid approach. And so this is the first time actually that we've been able to get in and get that internal structure. Okay, so.
Where's the SPH particle mass in between those numbers?
Sorry, the SPH particle mass is 30 solar masses.
That is what you mean by star particle.
Yeah, sorry. I should have said gas particle there.
But
The star particles are just a tiny bit less, just from mass loss. Okay, so I talked about this as a particle-based simulation. When you have high or lower resolution, the traditional way we do it is to treat a single star particle as it's a single stellar population. It's like a star cluster that evolves from a gas particle when it reaches a certain temperature, density, and other criteria. And you basically IMF average all of the properties, the winds, the supernova, and we use a Krupa IMF. But the problem is, once you start to get down to about 30 solar masses or anything less than 100, you can no longer represent a complete population, right? You're going to have a fraction of an O star and a fraction of a type 2 supernovae. So what we have to do now is stochastically sample the IMF. So now each star particle has a certain random sampling of these, and in the rare case that it's a massive O star, then this 30 solar mass particle is going to go around and it's going to behave as a single massive O star. It doesn't gain in mass, but it's going to have the full supernova explosion, and it averages out over all the particles to still conserve mass. And this has been tested at lower resolution by Kongyi Su, if you're interested in the details of that. Okay, so here's what I've gotten. The other problem with high resolution is you can't run that many of them. So in 2015, I ran 4 dwarfs, 2 classical. These are 10 to the 10 in dark masses, solar masses in dark matter. These are 2 isolated ultrafaints. In the more recent high resolution version, we also have 2 classical dwarfs and 1 ultrafaint. And as you can see, kind of the main point of my thesis was that every one of the massive dwarfs here has a satellite galaxy. So we predict satellites around isolated classical dwarfs. But more generally, in 2011, we formed, in fact, there are 2 satellites, which you can see here in the triangles. We formed 11 galaxies total in the high resolution region, so some ultrafaints that are isolated in their own right, but still in the high resolution region. And these all have 100 star particles or more. And you can see here, there's the abundance matching relations expanded from higher mass. So using these simulations, we make a prediction. So we make a prediction that galaxies exist in all dark matter halos. So every dark matter halo greater than about 5 times 10 to the 8 is populated by a well-resolved galaxy, 100 star particles or more. Now, that's not testable. I'm interested in making testable predictions, or it's not testable yet. So we predict that there should be satellites of isolated dwarfs, and these things should be everywhere in the field. Once we have the ability to find these ultrafaints outside of the virial radius of the Milky Way, we predict many hundreds of them, depending on if you mean as satellites of more massive dwarfs or not. So these things are everywhere. However, I'm sad to say, I still don't have a prediction for the minimum mass of galaxy formation. That's one of my primary goals, and yet, in order to figure that out, we have to push farther down. Here, this is my particle limit. This is 100 particles. This is the more broad stellar mass-halo mass relation. You can see galaxies are forming in dark matter halos, or single star particles, depending on what you want to call a galaxy. Single star particles are forming in tiny dark matter halos. So what your minimum mass is always going to depend on your resolution and depend on what you consider a galaxy. This will be my next paper. Will be investigating this lower mass end. I'm going to drop the particle count and look at the extreme mass of galaxy formation. So this is for one galaxy. This is one of my classical dwarfs. This is a stellar mass-halo mass relation for everything that forms at least 1 star particle. Here's where I cut off from the previous plot. Here, this is just everything that's 100 star particles or more. But if I get rid of that limit, then this is what I get. So these are the ones from this one halo, and this is everything that forms 1 star particle or more. Yes, in a subhalo. Yes, in a subhalo. You can see them here. They're very beautiful. One other cool thing we can do with this higher resolution, so these are kind of very simple images, but my colleague Shea Garrison-Kimmel, who makes all the beautiful fire images you might have seen, has mocked up a false color image of what this dwarf would actually look like in real life. You guys ready? I don't know what you were expecting. This is a tiny dwarf galaxy. They're not that interesting visually. It's density, temperature, self-gravitation, genes unstable, and molecular fraction.
And these wouldn't be disrupted by the tidal field of the disk?
They vary. Some of them, it depends on its orbit, and that's actually my big project for my next postdoc is going to be smashing these things into a Milky Way to see what happens. Because that's the one thing. I mean, I would say that's the main thing missing from my simulations, and it's going to come up again, but it's hard to do that with this kind of resolution. Yeah, sorry.
Well, if we're at the time thing, do the elliptical galaxies have a lot more dwarf galaxies because they don't have because they have a smooth potential?
Well, yeah, it depends on if they at equal mass.
Well, I don't know.
Yeah, because they'll have more if there's just higher mass. By nature of being higher mass, they'll have more substructure.
Okay.
So
but observationally, can you use that? And since they have soft potential as a discriminant in whether the disk tidal field is the opposite.
yeah, you could probably do that for the same. You'd have to mass match them though, so that might be difficult. Okay, so one cool thing we can do with 100 stellar particles that I wasn't so much able to do before is to put these things on a mass size plane. So this, again, is a half mass radius, or you could say half light radius, stellar mass, and all the black open circles are classical observations of dwarfs. The black points with error bars are the DES, year 1 and year 2 result. And I want to point out, like, if you want to put a simulation on this plot, you need to be able to resolve it, right? You can't, what's the half-light radius of a single star particle? And just to give a sense of where kind of standard simulations lie, I'm going to put the resolution spatially in mass for a couple simulations you might have heard of. This is a big box simulation, illustris. So it has a particle mass, nearly 1 million solar masses, and a spatial scale of almost a kiloparsec. Now, it's not designed to do this, of course. It's a big box simulation. It does a lot of other stuff, but just to give you a sense, you would only be able to look at this portion of the plot. Dwarf simulations, until recently, got a little better. They were able to get to about 100 spatial scale and 10 to the 4. But again, even if you're falling in this region, you might just be a single star particle, and you can't get these DES dwarfs. Even our own latte simulation, which again is a Milky Way simulation, but it's one of the highest resolution Milky Way simulations, isn't doing much better. The scales that I'm talking about are off the plot, so we're well able to resolve this. Okay, so the high mass objects that I've placed on here, these are just the low resolution versions. Everything in the high mass end actually lies right on top of these observations. And in fact, they form a really nice line, right? There's kind of just going along like this, almost suggesting some sort of trend between half-light radius and stellar mass. And in fact, a universal trend between at least halo mass and half mass or half-light radius was proposed back in 2011 by Andrei Krasov, and it's over many orders of magnitude. However, you can see these objects are really kind of bunching up. Oh, I should point out, these lines here are lines of constant surface brightness. So this is 30 magnitudes per square arc second, and what I've marked as very dramatically as unobservable is 32.5. That's probably where LSST can just about get to in terms of surface brightness, right? So if you can imagine for the same stellar mass, if you have more spread out, you're going to have a lower surface brightness. Okay, so this suggests, though, that maybe this is nothing more than a selection effect. Let's see where our tiny ultrafaints lie on this plot. I'm going to put them down. Oh, they were actually there the whole time. They're really, really puffy. They're really puffy. These things have, some of them nearly a kiloparsec in half mass radius, definitely a few hundred, a good, nearly order of magnitude or more higher than observations. But, maybe that's not so crazy. There have been all sorts of new discoveries in the low surface brightness sky. The most famous being the ultra diffuse galaxies. And these objects are known for having basically the mass of dwarfs, but the half-light radii of the Milky Way. They're much more massive than the objects I'm talking about, but they have very low surface brightnesses.
Does that mean there could be a too many satellites problem?
There definitely could be a too many satellites problem, and that would be one way we could maybe err on the side of, well, no. Yes, there might be a too many satellites problem. They definitely could be. These objects, yeah, so I hope to find out more about that. But yes, we used to call it the found satellites problem, which too many satellites is probably better. It's not the found satellites problem. But it's possible, it's definitely possible. Okay, so Oh, yeah, and even more recently, the lowest surface brightness galaxy ever detected was with the Gaia data release 2, Antlia 2. I've placed it, it's got a surface brightness of 32.3 magnitudes per square arc second, which is somewhere, in between here. It's, again, more massive than the objects I'm talking about, but it suggests maybe this apparent trend between mass and size is really a selection effect, and we just can't see all the objects up here, right? And if they are out there, yeah, hopefully we might be able to see a few of them with LSST. Okay, so I think I've at least convincingly explained why we can't see any of these observations up here, but you're probably wondering why we don't see any of the simulations down here, right? Why are all of my galaxies puffy? It is possible, and this is something I'd like to look into about possible numerical heating. If you want to talk to me about that. Joe and I were talking about the possibility because we use different dark matter and stellar masses. Anyway, sorry. So why don't we see any object here? So one thing I wanted, on this theme of selection effects that I think I've been mentioning at least twice in my talk, so we'll call it a theme. On the theme of selection effect, I thought, maybe this is a selection effect. What if, let's say we have a surface brightness profile of our dwarf galaxies, and what if we can only see the inner bright center of these objects? What if, we do a surface brightness limit? So I'm going to pick, there's two numbers on here. I'm going to pick 32.3 magnitudes per square arc second in honor of Antlia 2, right? What if we can only see these bright centers? Where would these objects move on the chart? So keep your eye on the colored points here. Woo, okay, that's quite a difference, right? So if we limit these things, the 32.3 magnitudes per square arc second, they move along lines of constant surface brightness. But look, our higher mass ultrafaints do start to go over towards the DES dwarfs. This is just the very preliminary work here, but it could be that some of the DES dwarfs are actually more the bright centers of more massive dwarfs with undetected stellar halos beyond observational limits. I'll be looking into this more in the future. Again, this would mean, could mean all sorts of things in terms of how we're misunderstanding the properties of these objects.
Isn't there a distinct difference that yours are isolated? Yours are isolated.
Yes. That's also, yes. That's,
okay.
Yeah.
The other related question is,
They could be stripped.
Definitely all, this is half mass radius stars, right? In terms of what's going on with the gas.
Yeah, it's just stars and half mass radius.
One of the key points of the Shapley-Curtis debate that the external galaxies were too small compared to the Milky Way.
Mm-hmm.
Surface brightness.
Yeah, I would say one of the weaknesses of my work so far that I'm going to correct soon is the lack of a Milky Way. I'm in some ways comparing apples to oranges, but it's really the best we can do now. Okay, so still on dark matter. How else can dwarf galaxies teach us about? This is dark matter part 2. Yeah.
Back on that slide.
Yep.
Really quick. Once you find, can you go back?
Oh, back on that slide,
Once
yeah.
you find a dwarf galaxy, which is, you're limited by your surface brightness, but then you shouldn't be able to define the half-mass radius because then you're just counting stars associated with the thing.
Yeah, you have to, there's a lot of, yes, you have to decide what your galaxy is, basically,
But
first,
it's
you
not
mean?
clear that the observations actually have this limit.
Yeah.
Once dwarf galaxies
That's true, we
found,
should, yeah, well, they might be missing stars, too.
could be missing stars.
Yes, well, yeah, and that's what I'm suggesting might be happening. I spoke with Josh Simon and Alex G about it at Carnegie. It's something I can look into. And they said it might be easier to preferentially miss stars on the outskirts of these objects. Again, it's not really a surface brightness cut, it's effective surface brightness, but okay. All right. Again, so don't worry, this is the second part of dark matter. Okay, so I didn't write it out here, but another challenge to the Lambda-CDM at the low mass end, maybe that doesn't produce so many groans yet as the missing satellites problem, is the core cusp controversy. And this suggests, basically this came about when we looked at the density profile in dark matter only simulations. And when that was done, it was found they had a steep cuspy density profile at the center. And this was, at all galaxy masses. However, when we measured the dark matter density from galaxy rotation curves for some dwarfs, it's just not the case. It's much shallower. It's a flat, low density core. Now, this is another way we can sort of use dwarf galaxies to distinguish between models, because although there's a Lambda-CD, there is potential way out that I'll talk more about something heating up the dwarf galaxy. Another way out is to allow dark matter to have some sort of self-interaction cross-section, allow it to scatter off itself. If it does this, then it heats itself up and creates dark matter cores, at least for dark matter only simulations over a wide variety of halo masses. Okay, but again, back to Lambda-CDM. This is what I do, is I try to see if we can solve these problems within Lambda-CDM. I'm not wedded to it, but that's just so far what I'm looking into. Because only if we can make these firm predictions do we know if the model is correct or not. Okay, Ponson and Governado have this really nice little cartoon that shows how baryons can heat up the dark matter, creating a core. You have your star particle orbiting a clump of gas. Supernova goes off. Very quickly, gas is blown out, so the star particle moves out. The gas falls back in slowly, so the stellar particle stays at its orbit. If you do this, if you keep blowing the gas out, having it fall back in, blowing it out and having it fall back in, you can create a dark matter core. This is shown in many different simulations by many people, but I will point out some work by someone at FIRE. TK Chan, I also think is almost not at UCSD anymore, basically showed, and I've just shown some of them here, that for about 10 to the 11 solar masses in dark matter, a little bit for 10 to the 10, and a little bit less for 10 to the 12, you can form these cores in dark matter. And it really, 10 to the 10 solar masses, which is the classical dwarfs that I've been telling you about, is right at the sort of transition between ultrafaints, where in fact they're not predicting cores in ultrafaints, and 10 to the 10, where you can form a core. Now, this is one way, it's been suggested, that we can distinguish once and for all between self-interacting dark matter and non-interacting dark matter, is if we find a core in an ultrafaint dwarf galaxy. So you can,
the reason for its result is just that star formation is too inefficient in the low mass things?
Yeah, it's basically a, yeah. It depends on the stellar mass to the halo mass relationship, shown by Ariana DeCintio here. There's just too much dark matter. The potential well is too deep for it to really have much of an effect. And then at higher mass, you have kind of explosions going off. It's not blowing all of the gas out of the Milky Way and back in again, right? It's just kind of popping off in the spiral arms. That's why there's really a key stellar mass to halo mass relationship, where you have a core of you get the best between about, for a stellar mass to halo mass relation, be about 10 to the minus 2 to 10 to the minus 3. Okay, so my simulations do form. We're really kind of right at that transition phase. So we do form one core. And this is the only galaxy that has a stellar mass to halo mass ratio of above 10 to the 4, to about 10 to the minus 3. And it's you see it's a pretty good core, particularly higher res, but that's just because it forms a little more stellar mass. And everything else has cusps down to about 100, at least 100 parsec. So you can see this is the density is a function of radius. This is where basically, I think it's a little more strict than the power criteria, where we consider it resolved, where we can trust numerically our results, and you see we have cusps. Okay, so we can form cores. Great, everyone can form cores. This is the more important point that I want to make. This is our lowest dark matter halo mass of any of our galaxies that form. It's only 2.7 times 10 to the 7. It does form a little bit of stars, but it definitely has a stellar mass to halo mass ratio of way below 10 to the minus 5. There's kind of a core there. I just want to point out, it's not going to break Lambda-CDM if we see tiny cores. I want to point out, when people talk about cores, they're talking about kiloparsec scale cores. I want you to remember this. I want you to remember this so much, I did a really terrible haiku here for you guys. It's really bad. Ultrafaint core scene, less than few hundred parsecs, Lambda-CDM. So remember, it's okay. It's good. I tried to make it better than that. I apologize. Okay. All that time, 40 minutes, I spent on dark matter. I'm going to now kind of go quickly through the last two ways that dwarf galaxies can teach us about reionization and then stellar feedback. Okay, so I already talked about how early in the universe, the ionizing background would have prevented the gas from cooling into the smallest halos. This was shown in 2000 by James Bullock, who showed that basically if all galaxies that form after reionization below a certain mass don't form, and you can actually match the number of satellites with the observable halos at this mass. So this may help solve the missing satellites problem, but what effect does it have on the galaxies that do survive? ultrafaints have, as shown by Tom Brown et al. In 2014, uniformly ancient stellar populations. These are 6 ultrafaint satellites of the Milky Way. Again, they're all Milky Way satellites, and they have identical color magnitude diagrams consistent with all having their star formation shut down by redshift of 2. And this is about where the epoch of reionization occurs, so it's one way to interpret this is, hey, that's reionization. However, they're satellites, right? I've heard people, many people say, oh, they all got shut down when they fell into the Milky Way. It's hard to distinguish because we only have Milky Way satellites. So some work that was done by Katie Rodriguez-Wimberly at UC Irvine used dark matter only simulations to look at the infall times of the dark matter halos we think host ultrafaints. And even if the abundance matching is a little off, you can see this is the probability that they fell in by a certain redshift. The probability these objects fell into the Milky Way or any host, this is for all 6, the probability that all 6 fell in by redshift of 1, let alone 2, is less than 1%. So that's one way to do it, right? These things all fell in, at least some of them fell in after redshift of 1. This is the way I want to do it, is I can actually just look at the galaxies that form in my simulation. So here's their stellar mass-halo mass relation, color-coded. This is the cumulative fractional star formation history. I'm just going to color-code it. All the ultrafaints are in cyan, all the massive galaxies in magenta, and you can see every ultrafaint, and again, there's no Milky Way at all, so now there's no Milky Way to fall into. We do have some satellites, but they're satellites of dwarfs, and all of them have their star formation shut down prior to redshift of 2. Meanwhile, the more massive galaxies have ongoing star formation almost to redshift of 0. One of the higher mass ones does actually self-quench. This is interesting. It kind of freaked me out at first, but this is lower than the, if you know anything, this is lower than the mass at which everything should be star forming, according to Marla Gia's work. There are some galaxies, classical dwarfs, that are, we think self-quenched, only like 2 or 3, but. Anyway, so these things almost certainly had their star formation shut down by reionization. So I make another testable prediction. Eventually, when we find an ultrafaint that's not a Milky Way satellite, I predict that they will all have uniformly ancient stellar populations. And if you're not convinced, I worked on a project, a brief project that never really got published with Oliver Elbert, where he ran one of my dwarfs, ultrafaint dwarfs with no reionization, and indeed it does continue forming stars to redshift 0. And then he went on to do a little more detailed analysis using a Milky Way. I can't remember the mass resolution, but you can see this as stellar mass. This is, the line is the halo mass at which 50% of these objects are dark. If you change reionization from the earliest to the latest allowed by the Planck results. And it changes by, like 0.2 dex there. Anyway, so reionization is having a big effect on these objects. See, I told you that was going to be very short. Next one is a little bit longer, but not much. Okay. I think I can do it in 5 minutes. Okay, how did dwarf galaxies teach us about star formation and feedback? Well, the really cool thing to look at is the mass-metallicity relation. This is showing some updated DEMOS spectroscopy of the Fe/H versus stellar mass from Evan Kirby's recent work. And for satellites and isolated dwarfs and maybe for ultrafaints over many orders of magnitude mass, they're all seem to have a universal mass-metallicity relation. And, strangely enough, it's roughly continuous with the overall slope from higher mass. Now, more recently, I think I'm not the only one who has questioned Evan's decision to neglect this point here and fit a universal profile to it. Many of us have decided this actually is a flattening, and if you add more points on there, it actually really does look like a flattening. But, you got to do what you got to do. So here are the data points again. Yeah, possible flattening. Okay, I have that here. So I'm going to put my points on here, and really myself and other simulations that are finally pushing down to these tiny, this high resolution are, for the first time, the ones who are putting these objects on the plot. And it's awful. It's really bad. We don't really get it up here, not exactly, and we're woefully off course here at the low mass end. I would like to point out that fire simulations, both gas and stellar metallicity above 10 to the 7, do match the MZR. So this is only a dwarf problem.
Just because in your simulation, reionization is having a huge effect, right? Which is what you're just arguing. But the data suggests that at the mass scales of ultrafaints, it's much more gradual.
But I think these things were also affected by reionization.
Yeah, but here it's like a flattening, whereas in your case it's like
Yeah, I mean, I think I'm going to point. I think the difference is more. Yes, is more the presence of a Milky Way. But I will. Yeah, I will get into that. Yes.
So are you comparing isolated?
Yeah, I have.
Milky Way satellites?
I have to. But yes, exactly. Yes. No, exactly. Very good. Yes, absolutely. However, we do have some isolated objects here. So this issue, and also it's just a few supernovae. We don't have explicit POP3 treatment. We just have a metallicity floor, and these are all at the metallicity floor, basically. Our yield tables are also very old, and they're not for low metallicity, they're for solar metallicity. The type 2 supernova yield tables are, we just haven't been able to tie it down for very, very low metallicity yields. So we're using like Woolsey and Weaver 1995 for solar metallicity. So that might have something to do with it. But let's talk about the point everyone made, which is the Milky Way. Yes. So this is not a published figure. It's a little messy. This is the same data again, Fe/H. But what I've done is I ran a very high resolution, like a triple lattice. This is 880 solar mass baryonic particles. I ran one to redshift of 4.5. And Andrew's actual triple latte had already passed 4.5. So they're a little bit lower resolution, but I'm going to show you where they go on this. This is where they start at so I'm going to show 986. Anyway, okay, you can see 98765. 98765. This is kind of where they go. And it kind of looks good for the ultrafaints. We're getting a few up there. And in fact, I also checked the gas phase metallicity of a few even lower resolution simulations. And about 20% of the IGM is enriched by redshift of 5, is enriched to this level. So it is possible. However, we have a big problem up at higher mass here. We're not really going to match here. Eventually, I'd like to extend this a little bit higher, but because eventually we do end up matching, and I'm not sure how that works. Okay, so it explains the offset for ultrafaints, but not for massive dwarfs. Again, this problem also occurs, we think, in alpha. At first, we thought it was our type 1 delay time distribution, but it's probably, again, these type 2 supernova yields. If this is true, this kind of testable prediction, I'll put a question mark at it. Isolated ultrafaints may have higher Fe/H than the satellites. We have to detect these isolated ultrafaints to know for sure. And then in my last minute, I'd like to just say that I'm not the only one to find this. And in fact, I'm only going to go over 2 papers. I think this was seen in maybe even as far back as Boville and Riccati, 2009, something similar to this. But I'm going to talk about 2 recent works. Frings et al. Used nearly as high resolution simulations as we have, very high resolution. Also, they ran to redshift 0 with gasoline, so similar code. They actually match at higher mass, so I'm going to look into a little more about what, exactly why that might be. I haven't investigated this fully yet. Now, they actually, one of the authors sent me an email and said when they first saw this, they assumed it was resolution, but then they saw my paper and they realized maybe there's a bigger issue. And then even more recently, this paper really blew me away. Oscar Eggert's latest work. They run one single ultrafaint, a 10 to the 9 in solar masses and dark matter, a bunch of different ways. And they look at, they have their fiducial, they do radiative transfer, they multiply their supernova energy. Their high res has 20 solar mass, so better mass and slightly lower spatial resolution. But it's a grid-based code. They even have radiative transfer. It's a completely different code. And you could see, so it's a little, the 2 plots are a little confusing because here the axes are different. But you can see my points here are these pale red ones. And actually, where we match in stellar mass, we also match in Fe/H, except for the radiative transfer. Their radiative transfer runs happen to match much better. But everything, all of the tracks run right through where my data points are. So they're still hitting the same mass metallicity relation, maybe just a little bit farther evolved. So I think this is a problem that's just starting to be discovered, and maybe it has a really easy solution. I mean, this is all new stuff. Maybe it's going to take a little bit longer. Maybe we need to wait for those low metallicity type 2 supernova yields. I'm not sure. It's probably just a Milky Way, but more work on this in the future. But it's something we definitely need to take note of. Okay, in conclusion, all right, using the highest, you had to add in another caveat there because of Oscar's work. Spatial resolution simulations, cosmological simulations run to redshift 0. I'm predicting there's all sorts of ultrafaints out in the field, hundreds of them. They just happen to be, including the satellites of dwarfs. I can't tell you the lowest mass for galaxy formation. I will continue to work on that. Even though they're everywhere, we can't see them, not yet, but hopefully with LSST or better algorithms. Yes, we can create cores in dwarfs, but maybe tiny cores in ultrafaint dwarfs. So just remember, if there's already been some claim of cores in ultrafaint dwarfs, but depending on the size of the core, that could be completely consistent with Lambda-CDM. Dwarfs are ancient, independently of whether they're satellites or isolated ultrafaint dwarfs. And there's this issue with the mass-metallicity relation. It's probably a massive neighbor for the ultrafaints, maybe both, maybe type 2 yields. We're going to look into including an explicit treatment of population 3 star formation instead of just a metallicity floor. Maybe that'll figure something. And then, just dwarfs are awesome. Lambda-CDM's fine, but we should keep challenging it. It's very important to challenge it. We're going to kill it or make it stronger. And it's time to start thinking about how to build bridges, computationally achievably bridges between just higher and higher particle size to actually forming stars. Because at some point, if we have a solar mass star particle, one might as well have a real star. But we need bridges between that in the meantime. Thank you. No, it's so I can show that. The tiny ones, the really tiny ones all form their stars by redshift of 10. The really tiny ones, and the more massive ultrafaints form their stars by redshift of 2. So they have a little bit of there's like a subgrid self-shielding approx. I didn't need to unplug it. So you can see. Here it's color-coded, but so this is what I was showing here. These things all form before reionization really kicks on. And then the higher everything is affected. You can see pretty much everything is rolling over, maybe not this one. Most of them are being affected by reionization turning on, but these things have some gas left and keep chugging along, but then they don't accrete any more fresh gas, likely.
And also a quick question with the observations for the ultrafaint dwarfs that are found in the field that aren't satellites.
We don't have any of those yet. No.
Have you looked at LEOSP? That's your closest.
Oh, yeah. I guess I'm sorry. I'm thinking of like tiny ultrafaints, but yeah, you're right. It's more massive though.
LEOSP?
Yeah.
Not that much more massive. Well, you're talking.
Yeah, but you're right. Well, ultrafaint is technically up to 10 to the 5. I see such differences, like even right here. So sometimes when I need to I told you about the nomenclature and then I'm messing it up. So yes, for the tiniest ones, we don't have any satellites, but yeah.
I mean, where I was going was whether they have any gas in them, because it seems like in terms of trying to understand what's going on with the metallicities, looking at a gas phase metallicity beside.
Yeah, they don't.
I mean, they could be quite offset, the stellar and the gas, and this could help provide clues as to what's going on.
Yeah, my ultrafaints don't have any gas. The higher mass ones do, but not the tiny ones.
Is there any way to test the hypothesis that the softening of the cuts is due to the dark matter becoming degenerate? That was my favorite theory.
What do you mean?
Oh, in other words, like the phase-space argument for the neutrinos. It's possible that the dark matter is fermions that are degenerate. And does that make any kind of prediction that's testable in terms of the profile? Maybe you know.
I don't know.
That's a great idea.
Okay.
And the Gunn and Tremaine thing, after reading that argument, why not? It might be that degeneracy is happening on galaxy scale.
Yeah, I don't know. I don't think, not with my simulations. But
Sorry. I was wondering if you thought about how your star formation recipe changes the stellar mass of the mass halos. For our one sheet, if she uses Charlotte's molecular hydrogen
Right.
based star formation,
Yeah, they're getting,
she gets very different results
right.
than if she just uses the highest density.
Yeah. Yeah, it was something I thought of because of Faraz's paper and also just a lot of things that's come up. I really need to go back and run all the standard fire tests that were run back in the day, because back then we weren't even really forming ultrafaints. So we have these have been tested on dwarfs, maybe one ultrafaint, like one higher mass ultrafaint, but I haven't looked at different prescriptions. I've just been using so far the standard fire. Well, I saw that what Egertz et al. Did, and I've been wanting to do that, just one ultrafaint and then just changing everything, but I haven't done that yet. But I imagine a lot would change. The interesting thing about dwarfs is when you change things, I mean, what changes and what stays the same, because even just sometimes a little bit of stochasticity can, even just running on a different machine can unfortunately change things enough. But that's why I'm going to run more of these. You need a sort of to get a statistical sense and and ask yourself what's robust. They're always uniformly ancient as long as I don't keep reionization on. That's one thing that doesn't change, for example. But yeah, that's something I need to do.
How much of your metallicity issue is maybe an issue of mixing?
We do have metal mixing now, yeah.
But are you doing it too much? I mean, if you spread the metals you're creating from supernova over too much gas,
yeah.
you're going to drop the metallicity too low. So.
I think that, I don't know if I'll be honest, I don't know if I checked this for the previous runs before we did metal mixing, but that would be something I could easily check. It would be a good comparison. Because I didn't look at metallicity in my 2015 paper. Yeah, back then, before we had mixing, we had a huge spike in the metallicity distribution function at the floor, but I don't know what the average would have been. We said we matched it back then, but again, I think we were averaging the abundances before taking the log instead of doing it the way observers do, which is taking Fe over H of each star and then averaging. Once we did that, that's when we noticed the initial discrepancy, but I have to check that.
Thanks for a great talk. One of your themes was that we could use these kinds of simulations to test the nature of dark matter. The simulations have a lot of moving parts.
Mm-hmm.
How do you convince a skeptic that you're not actually mistaken about galaxy formation?
Yeah, so, I mean, I think it is true that maybe the first order issues are galaxy formation issues, but I think, again, with a large enough sample size and statistically, you can start to get control on those things. And if you hold all else equal and change the dark matter, you also see differences. So I think dwarf galaxies or ultrafaints are really good for ruling out models. So maybe it can't say this is specifically it, but you can test a dark matter model on it and use dwarf galaxies, I would say, to rule out a class of models and to maybe narrow in. So maybe you always have to make, there's always some uncertainty with your galaxy formation. And to be honest, we're really learning about star formation. That's really the biggest uncertainty. But through a combination of running, a suite, holding things fixed, all fixed but the dark matter, I think you can rule out some parameter space in terms of dark matter. And eventually as we go on figuring out galaxy formation better, then we'll have even more constraining power.
I'm sorry.
Mm-hmm.
Go ahead.
Can I just a quick question?
Mm-hmm.
He's had a lot of time on. So I know they're not particularly well resolved, but you also said that you formed a lot of stars in much, much less massive halos.
Mm-hmm.
When did those stars form? Because you would think that those would be the most sensitive to
that's a really good
heating, for example.
Yeah, that's a really good question, and I should check that, but I would imagine they all formed before reionization.
Right.
That would be, yeah. Where is that? Here it is. Yeah, I haven't, maybe a long time ago I looked at something like this for lower resolution, but I don't remember off the top of my head. But, yeah, I mean, if it's just a single star particle, like, how do you... It could just be passing through. It could be these things have stellar halos too, especially for a satellite. But so I wouldn't trust it. But even, yeah, I would expect all of these to be uniformly ancient. But I'll check.
Last question. Sorry, I'm hounding this, but there's so many interesting things. Just like on degeneracy, I think that would make a relatively specific prediction of the density, like white dwarf. you test that that way?
Yeah, I mean, well, the thing is, we already know the Milky Way is shredding up dwarf galaxies into streams, but what you're talking about is even like empty dark matter halos, right?
Yes.
The subhalos themselves are getting destroyed. So I don't know. I don't think we would be able to detect that. But we do see streams, and with Gaia, like according to the conference, and what I've seen, there's a ton more. So that is happening.
If there's way more than they, you know, it's
Yeah, we have to at some point factor that into our missing satellites problem, probably.
Let's thank Coral again.
Okay. Thank you.